Hello, everyone. Good evening to everyone. So, as you all know, that today we will going to continue with our chapter, which is NCRT Chapter 2, Electrochemistry. And today we will going to cover its part 2, right? Part 4. Okay. So, NCRT Chapter 2, Electrochemistry Theory, Part 4. So, let's start. First of all, disclaimer. The images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creator and owners. If you are the owner and have any concern or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of content may have been generated using the generative AI, which is experimental. Okay, let's start. So, today's objective. So, today's objective is that after studying this lecture, you will be able to describe the method for measurement of conductivity of electrolytic solutions and calculations of their molar conductivity. Also, you will be able to justify the variation of conductivity and the molar conductivity of solutions with change in their concentration and definition of the symbol which represents the molar conductivity. Okay, so info for J, I don't know, I didn't understand the query. Okay, if you can clarify it more. Okay, let's continue. So the topics to be covered according to the NCRT in this lecture are, first of all, the conductance of electrolytic solution, which is our section 2.4 in our electrochemistry chapter in the NCRT textbook. Then we will study the subsection 2.4.1 of the NCRT textbook, which is measurement of conductivity of ionic solutions. And lastly, we will cover some examples from 2.4 to 2.5. That means 2 examples. Okay. So, is it sufficient for your JE preparation or JE examination? It is kind of, but you have to practice more. And if you will not be able to clarify your doubts in this lecture, or you will be, want to study more or know more about about this topic, electrochemistry, then you can refer some other books other than the NCRT, and you can also solve the PYQs provided by the SATHEE and some other sources through some other sources, of course, for your that will be helpful for your JE preparation. Okay. So the first topic we will cover is conductance of electrolytic solutions. So in this, let's talk about the current due to the electrolytes. So the flow of electricity through the solutions of electrolytes is due to the migration of ions when the potential difference is applied between the two electrons. So if I tell you that we have been covered a lot in this chapter already in our previous lectures, where we have studied studied about different cells, how they work, what are the function, how the electron will migrate from one electrode to the another electrode, what is the structure of the cell and the type of cell, and what have been we have studied. So many things have been so many things or the topics have already been covered. Standard potential, electrode potential, okay, cell potential, Nernst equation, this all we have already been studied. So continuing with that, in this point it is given that flow of electricity through the solutions of electrolyte. Solution of electrolyte means, if you remember the cell structure, we have a beaker in which some solution is present where the electrode is dipped into it, right, which is connected to some other electrode, and through this wire the two electrodes are connected, and through this wire the current will flow, or the electricity will flow. So the electricity flow through solutions of electrolyte. We are talking about this solution in which our electrode is dipped. So the solution of electrolyte, the electricity flow through this solution of electrolyte is due to the migration of ions. That means the migration of ions is the point, or migration of ions is the reason that the ions from the electrode, one electrode to the another electrode, are migrating, right? Because cell is following some redox kind of reaction in which one species is reducing and another species getting oxidized, right? So the migration of ions, the interchanging of ions is happening. So that is why we are saying that due to this migration of ions, the electricity of the flow of electricity is possible through the solutions of electrolytes. And when the migration of ions happens, when the potential difference is applied between the two electrodes. Okay, if the two electrodes are connected by the wire, they have their potential difference between them. So we are applying some potential difference between the two electrodes, through which the migration of ions is happening, and due to which the flow of electricity through the solutions of electrolytes is producing. Okay, the cations which are positively charged move towards the negatively charged electrode called as cathode. So basically the cations are the ions. Okay, first of all, ion is what? If we have a metal, any element, let's suppose it is any element, when it gains or loses the electron, it will become an ion. That means this ion will be going to have some charge. Initially, it is in the neutral form. Okay, and finally, after losing or gaining of electron, it will become an ion having some either positive or negative charge, depending on whether it is donating or accepting the electrons. Okay, now the ions are divided in two categories: the cation, about which we are talking in this point, and second one is anion. The cation are having the positive charges, and the anion are having the negative charges. Positive charges because it has loosened its electrons. Negative charges because it has gained some negative charge, or it has gained some electrons to become negative. Here we are talking about cations, that the cations which are positively charged will move towards the negatively charged electrode known as cathode, while the anions, that means the negatively charged ions, which are negatively charged, move towards positively charged electrode called as anode. Okay, now the as you know, the law of attraction, that the positive attracts the negative and vice versa. So the cations which is having positive charge move towards negatively charged electrode, and this negatively charged electrode is known as cathode, while the anions which is having negative charge moves toward positively charged electrode, and this positively charged electrode is known as anode. Now let's talk about the conductance. Because we are talking about electricity, so conductance is important to understand. Resistance, as we know, is the hindrance offered to oppose the flow of current. Okay, there is a thing named resistance. There is a property which is resistance, which oppose the flow of current. Okay, if somewhere or in a wire, let's suppose between two electrodes, if a wire is connected and through this the flow of current is from here, from like anode to the cathode, let's suppose, okay, let's suppose that current is flowing in this direction, then resistance will oppose the current flow of current in this direction. So resistance is the property which always offer the opposing nature or opposing force to the flow of current, which always try to stops the flow of current. The ease with which electricity flows through a solution is called the conductance, represented by capital G of the solution. So for any solution, through the solution, the ease with which the electricity is flowing through the solution. Okay, so how easily the electricity is flowing through the solution is the property of the solution, which is known as its conductance, which is represented by capital G. And it is defined as reciprocal of resistance capital R of the solution. That is, you can also write capital G equals to 1 by R. Okay, so conductance equals to 1 by resistance. This is the equation, NCERT equation 2.18, marked as 2.18 in our NCERT textbook. Now it is expressed in the unit called reciprocal ohm, because the resistance, if you studied this in the physics, okay, so resistance has the unit in ohm. Okay, the symbol of ohm is this much, this, and the R, if you can write this symbol, it will be OHM, ohm, right? But here we are defining the conductance as inverse of the resistance, that is 1 by R. That means the unit for this conductance will be the reciprocal ohm, that means ohm to the power minus 1, G. Okay, here G will come. So for G, the unit will become ohm inverse or ohm inverse. Okay, both are represented as ohm. And in the SI system, standard unit system, the unit of conductance is taken as Simon, which is represented by capital S. Okay, so your syllabus will take so much time, as we are covering each chapter in some days, right? Depending on whether our chapter is lengthier or shorter, or. So depending on that, one chapter is taking maybe max 10 days to 8 days to 10 days. So depending on that, your syllabus will be going to complete till November, I think so. Okay. Okay, so let's continue. So specific resistance. Let's now study about specific resistance. We have already covered about conductance. Okay, we have already covered about conductance represented by capital G, which is equals to 1 by R. And now let's talk about the next topic, which comes under the section 2.4 of NCERT textbook. So the topic is specific resistance. So the electrical resistance of any object is directly proportional to its length, that is L, and inversely proportional to its area of cross section, that is capital A. Okay, so the electrical conductance, that means the electrical resistance of any object. So resistance is directly related to the length of the wire, okay, or the length of the object through which the resistance is applying. So directly proportional to the length, that means if length will increase, the resistance will increase. Okay, and resistance is inversely proportional to the area. Okay, that means what is the area of cross section of that wire or object. So if area is increasing for the wire or object, the resistance will decrease. So that is the relation between the resistance, length, and area of the object. So you can write it as R is directly proportionality sign L by A, because it is directly proportional to L, inversely proportional to A. So you can write it like this, 1 by A. Okay, R directly proportional to L and inversely proportional to area. And when you combine it, you can write it as R proportional to L by A. Right? And when you remove this proportionality sign, a constant will come with equal to, which is called as rho. Okay, rho L by A. So this is the equation. R equals to rho L by A. R is resistance, rho is constant, and L by A is the fraction of length and area. Okay, and this equation is NCERT equation 2.17, marked in our NCERT textbook. Okay, so rho is constant, which is depending upon the nature of the material, and it is called specific resistance of the material. Okay, so rho is a constant and its value depends on the material nature, whether it is rough or what is the nature of the material, basically elastic, non elastic. So rho is a constant and it is depending on the nature of the material, and it is also called its it is called as specific resistance of that material. Okay, if you find the value of rho will be Ra by L, right? So specific resistance. Okay, now if we have L, that is length, as 1 meter and area as 1 meter square, so rho will become equals to the resistance. Okay, if you put the length as 1, area as 1, okay, then rho will become equal to resistance. Thus, the specific resistance is defined as the resistance of specimen 1 meter in length and 1 meter square cross section. Okay, for any species, for any material, if it is 1 meter in length and 1 meter square, having 1 meter square cross section, then the resistance of that material is known as specific resistance. In the other words, it is the resistance of 1 meter cube of the material. So there are many ways to write a particular thing. So basically we have a formula for the resistance like this, where we introduce a new term which is specific resistance, which is rho. You can define the rho from this formula also by putting different values of L and A. If you put the L and A value as unity, then you can define the standard definition of the specific resistance. So specific resistance is defined as the resistance of 1 meter cube of material, or it is the resistance of a specimen which is 1 meter in length and 1 meter square in the cross section. Okay, yeah, we can expand the conductance formula, and I'm saying that in the coming lectures or in the coming slides you will be able to expand many of the formulas which we will going to study in this lecture and in the further later lectures. Okay, in different ways, because all the formulas are kind of interrelated, because somewhere resistance are coming. Now resistance we have just defined as specific resistance multiplied by L by A. So wherever the R will come, you can put that equals to rho L by A in that formula, right? So you can expand the formula by using the other formulas which you will going to study. Okay, and this is the chapter, that is electrochemistry, and this content we are studying from NCERT, so you can consider this for the JEE and the NEET both. Next topic is specific conductance. So the reciprocal of the specific resistance, that is 1 by rho, is called specific conductance. Okay, specific conductance. So conductance is defined as capital G. Now specific conductance is 1 by rho. That is 1 upon the specific resistance. This may be defined as conductance of 1 meter cube of a material, right? Because rho can be defined as the resistance of 1 meter cube of material. So the conductance or the specific conductance can be defined as the conductance of 1 meter cube of a material. Now it is generally denoted by this kappa. Okay, this is a symbol known as kappa, maybe some other name. So this is used for representing the specific conductance. Thus, we can write that kappa equals to 1 by rho. And see, as I said, that you can put the formulas relatable in any formula to expand that. So rho we know is equals to R L by A. So we just put the value. So L by A times 1 by R, and it will be L by A times conductance, because 1 by R is conductance. Remember, G equals to 1 by R. So this is conductance. So L by A times conductance. The units of specific conductance are Simon meter inverse. Okay, Simon meter inverse, because conductance has a unit of Simon. So it is, you can write it as Simon, and length has the unit of meter if you take in the standard SI units. So meter, area is meter square. So 1 meter will cancel out, this meter will go in the numerator, and the whole unit will become Simon meter inverse for the specific conductance. Okay, so this class will go up to probably up to November. or December. Okay. Now let's focus to the today's lecture. The next topic we will going to cover under the section 2.4 of our NCERT textbook is equivalent conductivity. So specific conductance, although a suitable property for the characterizing metallic conductance, is not so far characterizing electrolytic conductance, where the value amongst other things depends upon the concentration of the solution of the electrolyte as well. Okay, so what we are saying that the specific conductance you have just studied represented by kappa, although a suitable property for the characterizing of metallic conductance, is not so for characterizing electrolytic conductance. Okay, so specific conductance you can use for defining the metallic conductance, right? Because if you have a material made up of any metal, and if it is having any length, any conductance, any resistance, any area, then you can define the specific conductance for any metallic conductance. But it is not for defining the electrolytic conductance, where the value amongst the other things depends upon the concentration of solution. Because in the electrolytic conductance, we are talking about the solution of the electrolyte, right? So we don't use specific conductance to define the electrolytic conductance. Now, while measuring conductance of electrolytes in the solutions, another quantity of much greater significance known as equivalent conductivity, and it is frequently used. Okay, so when you measure the conductance of the solution, or you can say electrolyte solution, some other quantity which is having greater significance, greater importance, which is known as equivalent conductivity, is frequently used. So for the metallic conductance, for the measurement of metallic conductance, for the defining of metallic conductance, you can use specific conductance, that is kappa. But for defining the electrolytic conductance for electrolytes in the solution, we use equivalent conductivity. It is defined as the conducting power of all the ions which is produced by 1 gram equivalent of an electrolyte in a given solution. So it is also denoted by delta. Okay. So how can you define the equivalent conductivity for the solution or electrolytic solution? So it is defined as the conducting power of all the ions, because we are talking about the electrolytic solution. That means the solution having the ions present in it. So conducting power of the ions, which is produced by 1 gram equivalent of an electrolyte in a given solution. In a given solution, the solution is made up of some electrolyte, right? So if we have a 1 gram equivalent of an electrolyte, the ions which will be produced by that electrolyte will be, and the conducting power of that ions in a given solution is defined as equivalent conductivity. And it is also denoted by the kappa. So delta equals to kappa times psi, where psi is the volume of the solution in cubic meters, that means meter cubic. Okay, cubic meters. So psi is the volume of solution in cubic meters, which is containing 1 gram equivalent of the electrolyte. Okay. Now, what is the relation between the specific conductance and equivalent conductivity? So specific conductance, as you know, we use for the metallic conductance, and equivalent conductivity we use for the electrolytic solutions conductance, or you can say. Okay, so in order to work out the relationship between the specific conductance and the equivalent conductivity, so if you want to tell the relationship or the difference between the specific conductance and equivalent conductivity, let's imagine 1 meter cubic of a solution. This is a volume given for a solution, which is 1 meter cubic of an electrolyte placed between the two large electrodes 1 meter apart. Okay, so imagine we have a 1 meter cubic of solution of electrolyte placed between the two large electrode 1 meter apart, and we have two electrode which is having the distance of 1 meter between them. The cross sectional area of the solution will be 1 meter square. Okay, because as you know that volume is area times length. Okay, now volume we have given 1 meter cubic, area you have to tell, length you have given, the distance between the two electrode as 1 meter, the distance is 1 meter, so the area will also come out as 1 meter square. Okay, so the cross sectional area of the solution will be 1 meter square. Conductance of the solution will evidently be its specific conductance because we are having 1 meter cube of solution. So what we are trying to say that the conductance you will get after this, that you have considered a 1 meter cubic volume of solution of electrolyte in which two electrodes are dipping, which are 1 meter apart, and the area or the cross sectional area of the solution will also be 1 meter square. So the conductance you will get of the solution will evidently be its specific conductance because we are having 1 meter cube of solution, right? We have taken 1 meter cube, that means the unity of the volume. Further, let's suppose that 1 meter cubic of the solution contains 1 gram equivalent of electrolyte which is dissolved in it. Okay, so this is the weight of electrolyte which is dissolving in a solution to make it the electrolytic solution. So if we are supposing its volume to be 1 meter cubic, then according to the definition, the conductance of the solution will be equal to equivalent conductivity, that is represented by lambda EQ. Okay, so the conductance of the solution in this case will be equal to the equivalent conductivity. Thus, in this case, the conductance, that is G, will be equals to specific conductance kappa, which is equals to equivalent conductivity, which is lambda EQ. Okay, you can define the conductance as the sum of specific conductance. Okay, you can define the conductance equals to specific conductance and equivalent conductivity. Equivalent conductivity symbol is this lambda EQ, and specific conductance is kappa. Now let shift to our next topic, which is a subsection marked as 2.4.1 in our NCERT textbook, which is measurement of the conductivity of the ionic solutions. In this, first we have to understand about the molar conductance. It is customary to express electrolytic conductance in terms of molar conductivity, which is defined as conducting power of all the ions produced by 1 mole of electrolyte in a given solution. So, electrolytic conductance, we are just defining the electrolytic conductance in the term of molar conductance, nothing more. Okay, so electrolytic conductance in terms of molar conductivity, which is defined as conducting power of all ions which are produced by 1 mole of electrolyte in a given solution. We have a solution, remember we have a solution where the electrode is dipping, and solution, now this time lately for defining the electrolytic conductance, we have taken the volume of the solution as 1 meter cubic, right? Here, for defining the molar conductance in terms of the molar conductivity, we are defining the solution as having 1 mole of electrolyte. Okay, previously we have 1 gram equivalent of electrolyte. Here we are having 1 mole of electrolyte in the given solutions. So the ions which are produced by 1 mole of electrolyte in the solution and the conducting power of that ions produced by 1 mole of electrolyte is known as the molar conductivity. As the name says, molar. If anything is having molar, that means we are talking about its concentration, or in the terms of molar concentration, either 1 mole. Okay, we are defining the thing in the 1 mole quantity. Now it is denoted by this lambda m. molar conductance. Let us consider a solution which is containing C moles of an electrolyte in 1 cubic meter of the solution. So this is the number of moles of electrolyte, and this is 1 cubic meter of the solution, that this is the volume of the solution. The volume of solution containing 1 mole of electrolyte would be, okay, 1 by C cubic meter. What we are saying, let's suppose we have the volume of solution as 1 meter cubic and it is containing C number of moles of electrolyte. That electrolytes are which are dissolving in the solution to make it electrolyting. Okay, so if the volume is 1 meter cubic and we have C number of moles in of electrolytes present in that volume of solution, then the volume which is containing 1 mole of electrolyte will be 1 by C, right? We take this C in the denominator, so we just apply the unity method to determine this. So 1 mole of electrolyte would be present in 1 by C cubic meter of the solution. And delta M is the conductance of 1 meter cubic of solution. That means this much this much volume of solution conductance multiplied by the volume of solution in the meter cubic, which is containing 1 mole of electrolyte. Okay, so as I said, molar conductance, that means the 1 mole of electrolyte is present in our given solution. So the delta M is defined as, okay, so lambda M is defined as the 1 meter cubic volume solution conductance multiplied by the volume of the solution in meter cubic in which our 1 mole of electrolyte is present. So volume multiplied by the conductance, let's suppose G. Okay, so the conductance of 1 meter cubic of the solution multiplied by the volume in the meter cubic which is containing 1 mole of our electrolyte. This is the formula for the lambda M, that is molar conductance. Now lambda M is also equals to specific conductance multiplied by 1 by C. Okay, specific conductance multiplied by 1 by C. Specific conductance was G, which is defined as 1 by R, right? So okay, specific conductance is specific conductance we are taking in the place of this conductance of 1 meter cubic of the solution, which is defined as specific conductance, and multiply by 1 by C. Okay, C is representing the number of moles here. Okay, and this, that is lambda M equals to kappa by C, because specific conductance having the symbol kappa. Okay, so lambda M, that means the molar conductance equals to the fraction of or the ratio of specific conductance to the C, and this is the equation number 2.21, which is already marked in our NCERT textbook in the electrochemistry chapter. Okay, now the units of kappa we have seen is Simon meter inverse, right? And those of C are mole meter cubic. So the unit of lambda M will be, you can derive it. So kappa is Simon meter inverse divided by C is mole meter cubic, or okay, mole meter cubic. Okay, and no, it has -3. Okay, so concentration, concentration is the number of moles divided by the volume. That's why we have taken the volume as in the numerator, and it will become m to the power -3. Okay, so this is the unit for the concentration, this is the unit for the kappa. When you solve it, it will be Simon meter square mole inverse. This mole will come in the numerator, and this m to the power -1 and m to the power -3, this will when you solve it, it will become meter square. Okay, so Simon meter square mole inverse is the unit of lambda M. Okay, so So remember, this is the formula for the molar conductance, which is kappa by C, specific conductance by C, and its unit. Both are important in our further lecture. Okay, next topic is measurement of the conductivity. So let's define it, that how can you measure the conductivity for a solution or the conductivity. So measurement of ionic solution is not possible with a Wheatstone bridge. Okay, if you want to measure the conductivity for an ionic solution, it is not possible with the Wheatstone bridge. Firstly, passing the direct current, that is DC, changes the composition of the solution. When you pass the direct current, it can change the composition of the solution. Composition of solution means its concentration. Its let's suppose we have copper sulfur solution. Okay, so composition means it can change these ions present in this solution. Okay, so passing the direct current can change the composition of the solution. And secondly, a solution cannot be connected to the bridge like a metallic wire or the other solid conductor. Okay, so we are here talking about the measurement of the conductivity, right? Now, as I said, that conductivity can be metallic conductivity or electrolytic conductivity. Metallic conductivity for the metals, electrolytic conductivity for the electrolytic solutions. Right. Now, electrolytic solutions means we have a solution proper where some electrolytes are dissolving. It is having an electrode for the performance or for the passing of or the flow of the current and the movement or migration of the ions. Right. So, when you pass the DC current, direct current, it will change the composition of the solution. It can change the composition of the solution, right? It can affect. Secondly, a solution you cannot be connected to the bridge like a metallic wire or the other solid conductor. Bridge, we are talking about the Wheatstone bridge. So this is the, if you, we will see its structure and its diagram, where you can see that in the Wheatstone bridge, or you can say in the Wheatstone bridge, you cannot connect this solution or this electrolytic solution like a metallic wire or other solid conductor, as we have done in our normal cell structure, right? Because in normal cell you can see that we have two beakers or maybe one beaker. Sometimes one beaker is also there, in which single beaker both electrodes are dipped. We have a solution and they are connecting by some wire through the external circuit, and through external circuit the current is flowing. In the two beaker case, we have two electrodes in each beaker. They are connecting with the wire and voltmeter, and the current is flowing and the electrons is moving, and the current is flowing externally. Okay, so the solution, you cannot, if you are talking about the solution, you cannot connect it to the bridge like a metallic wire, which you done in case of the solutions, right? That you join the two electrodes with the wire. But here in the bridge you cannot do that, or other solid conductor. Okay, if you take a solid conductor, you can fix that in the Wheatstone bridge, but you can't fix the solution there. Okay, why? We will understand that. So the first difficulty is resolved by using an alternating current source of power. Okay. Okay. Now you have to understand this thing, that when you change, when you pass the direct current, it will change the composition of solution. As I said, that if it is having some ions, it will release some ions, right? Electrolytic solution will release some ions, cations and anions. It can change its composition. It can change the salt composition by the passing of direct current. But if you apply the alternate current, it can as a source of power. Okay, if you use the current as a source of power for generating the electricity and for passing the current and the electrons moving, so for that you can provide the alternating current. That will not cause any change in the composition of the solution. Okay, because direct current means you are applying direct electricity or you are applying direct current to the solution. Okay, in the solution, understand, in the solution. So if you have a solution, you are applying through a wire or something directly current to the solution. That is not possible, and that can change the composition of the solution. Okay, that can affect the solution because it is not, thing to consider. It is not a thing to consider. But if you need or if you use a alternating current, that means if you need a if you use a other source, like you are passing the current through some kind of instrument, okay, which you connect to the Wheatstone bridge or to the solution to pass the current through the solution for the passing of the electrons. Okay, in that case, we use alternating current as a source of power. So this is the main difference. The second problem is this. Okay, second problem is solved by using a specially designed vessel which is called as conductivity cell. Okay, so as I said that in the second problem, that the second problem or issue in the measurement of conductivity for the electrolytic solution through the use of Wheatstone bridge is that the solution cannot be connected to the Wheatstone bridge like a metallic wire or other solid conductor. And we have a solution for this, that we can use a specially designed vessel in which we can put our electrolytic cell, right? And then we can connect that to our Wheatstone bridge for the measurement of the conductivity. Okay, that specially designed vessel is known as conductivity cell. Okay. Okay, now let's define the conductivity cell, how it looks, what its structure. So it consists of two platinum electrodes which are coated with the platinum black. Finely divided metallic platinum is deposited on the electrodes electrochemically. Okay, so a conductivity cell is having two platinum electrodes, two platinum element electrodes, which are coated with the platinum black, and it is and finally divided metallic platinum is also deposited on the electrodes electrochemically. Now these have area of cross section equal to A and separated by the distance L. So the electrodes have the vessels have the cross section area equals to A, and they are separated, or the electrodes are separated by L distance. The resistance of such a column of the solution is then given by the equation. Now the resistance you have to identify. Okay, so the resistance for that column of the solution, that means that vessel is containing some solution which is nothing but our electrolytic solution present in our cell, right? So the resistance of such column of the solution is given by the equation R equals to rho L by A. This is the definition of resistance, right? So resistance is rho L by A, and rho is defined as 1 by kappa, so we write it as L upon kappa by kappa A. Okay, L upon kappa A. This is the equation 2.17, NCERT equation 2.17, marked in our NCERT textbook. So this is the figure or the diagram for the conductivity cell, figure 2.4. Two different types of conductivity cell are present. The first one is this blue one, second one is this yellow one. And the blue one, you can see we have platinum electrode, platinized platinum electrode. That means platinum black coated platinum electrode. Here also this platinized platinum electrode, and they are connecting through this connecting wires. Okay, and we have this vessel. Okay, in which the two platinum electrode are present. We have a vessel where our electrolytic solution is situated. Okay, that means this electrolytic solution is having the ions which we are going to produce. And this is another kind of conductivity cell where again the platinized platinum electrodes are there, this one, and they are connecting through the wires. Okay, and inside this we can hold our solution. So these are the two different types of conductivity cell. Now let's talk about cell constant. As you see that we have a constant thing. That means something is related to constant. Okay. So all the conductivity cell have known value of L by A because they are already specifically designed vessel for the measurement of conductivity of electrolytic solutions. right? That's why the conductivity cell have known value of their L by A ratio, which is called as cell constant, represented by G star. So G star equals to L by A, and L by A is the ratio which is already known for all the conductivity cells. And L by A, you can also write it as resistance time kappa. So G star is defined in both the terms. This is the NCERT equation 2.18 given in our NCERT textbook. Value of the cell constant, that is G star, is fixed for a given conductivity cell, right? Because G star is given as L by A. L by A is already known for the conductivity cell. So G star, that means the cell constant value, is already fixed for any given conductivity cell. Now the resistance can be written as R equals to rho times G star, because R equals to rho L by A. L by A is G star, right? So R equals to rho G star. Okay. So this is the value for the resistance which you can use, which we have derived from the cell constant definition. Next, we will going to see what is Wheatstone bridge. Okay, now let's understand this on the basis of which we have studied the cell constant, and we have studied that how can you solve the problem which we have seen previously while the measurement of molar conductivity of electrolytic solution. So once the cell constant is determined, that is G star, if you know the G star, we can use it for measuring resistance or conductivity of any solution, right? Because G star, or you can say rho G star equals to R. So you can define the resistance, you can define the conductivity or resistivity. Okay, so G star is we have already known, and we can use it for measuring the resistance or the conductivity of any solution. Now it means Wheatstone bridge. Wheatstone bridge consists of two resistances, R3 and R4, and a variable resistance, R1. Variable resistance means it can change the value. And the conductivity cell having the unknown resistance, R2. So 4 total resistance are already attached in our Wheatstone bridge, R1, R2, R3 and R4. R1 is having a variable resistance. Its value can change. And we have the R2 resistances of the conductivity cell, and R3 and R4 are other two resistance which are connected in the Wheatstone bridge. We will see it in the figure 2.5. So the Wheatstone bridge is fed by an oscillator O, which is a source of alternate current power in the audio frequency range from 550 to 5000 cycles per second. This is extra information provided for the functioning of oscillator. So Wheatstone bridge is also, get its power of working from the oscillator represented by O in the diagram. And P is a suitable detector, which is a headphone or other electronic device. And the bridge is balanced when no current passes through the detector. Okay. So a suitable detector, which is marked as P, which is either a headphone or other electronic device. So P is the suitable detector in the bridge. Okay. And bridge is balanced when this detector will show zero reading or no current will pass from this detector. This is the image, or this is the diagram for the Wheatstone bridge. This is figure 2.5, arrangement for the measurement of the resistance of a solution of an electrolyte. Okay, so for the measurement of conductivity or the resistance of solution of an electrolyte, we use this Wheatstone bridge where we have 4 resistances, R1, R2, R3 and R4. And R1 is a variable resistance and R2 is a resistance of conductivity cell. Okay, and P is a detector. Conductivity cell means the conductivity cell is having our electrolytic solution, remember. Okay, so this is the arrangement of the Wheatstone bridge. Now this point this joining point between the R1, R3 and R2, R4 are directly connecting through O, that is oscillator, through which the source of AC power is providing in the Wheatstone bridge. Now, continuing on that, and under these conditions, unknown resistance is R2, which is for the electrolytic solution. Okay, conductivity cell resistance. So R2 will be equals to R1, R4 by R3. This you can derive by using the resistance in parallel or resistance in series formulas, which you have studied in the physics. Okay, so R2 will be R1, R4 by R3. And this is the NCRT equation 2.19 given in our NCRT textbook. Okay, so this is the Wheatstone bridge we have seen. So R2 is the resistance of conductivity cell, and it will be defined as equals to the product of R1 and R4 divided by the R3. Okay, now let's do the problem. So this is problem 2.4, which is the in-text question provided in our NCRT textbook in this chapter. So the resistance of a conductivity cell filled with 0.1 mole liter inverse KCl solution is 100 ohm. So, the conductivity cell resistance is given as 100 ohm, and the conductivity cell is filled with this concentration of KCl solution. If the resistance of same cell when filled with this concentration of KCl solution is 520 ohm, calculate the conductivity and molar conductivity of 0.02 concentration of KCl solution. The conductivity of 0.1 molar KCl solution is given as 1.29 Simon meter inverse. So what we have been given that we have two solutions. No, we have a single cell, which is conductivity cell, filled with different solutions whose concentration is first 0.1, second is 0.02. Each is having different resistance. Okay, so the conductivity cell is having different resistance for different solutions, and you have to calculate the conductivity and the molar conductivity of the second concentration of KCl solution, and you have provided the conductivity value of first concentration KCl solution as 1.29 Simon meter inverse. Okay, so try to relate this question with some concepts which we have studied in this lecture and try to apply some formula. You have some time, try to analyze this question, and then we will continue to its correct answer. Okay, so let's continue to its answer. Okay, let's solve it. So for solving it, first we have to consider the given terms, and then we have to relate it with the formulas we have studied. So the cell constant is given by the equation. Cell constant, which is G star, equals to conductivity multiplied by resistance. Okay, this is the NCRT equation 2.20. So cell constant G star is conductivity times resistance. We have already given the okay, we have to identify the conductivity for the second solution, but we have given the conductivity of first solution. So we use the conductivity of first solution to determine the cell constant, which will be same for both the solutions. Okay, because the conductivity cell will be having the same resistance. Okay, in the case of one solution. So conductivity is given for the first solution as 1.29. So 1.29 Simon meter inverse multiplied by the resistance, which is 100 ohm for the first solution, right? So we put it in the formula, and then when you solve it, it will be 129 meter inverse. So this is the cell constant G star, which you can also write it as 1.29 centimeter inverse. Okay, in the different units. Now this we have derived the cell constant. Okay, the in the question we have given that you have to identify conductivity and molar conductivity, and in determining these two terms we will going to use the cell constant value. So conductivity of the second K cell solution with concentration 0.02 will be equals to cell constant upon the resistance. Okay, so cell constant we just determine and resistance we know because it is given. So conductivity will be G star by R. G star we just find out as 129 meter inverse. The resistance for the second solution is 520 ohm given in the question. When you divide this or when you solve this fraction, this will give the conductivity of the solution. Okay, this is the NCERT equation 2.20. So the conductivity is coming out as 0.248 Simon meter inverse. And the concentration already given as 0.02 mole liter inverse. Okay, and you can also write it in the meters as 1000 multiplied by 0.02 mole meter cubic per cubic. It will be 20 mole per meter cubic concentration of the solution. Now, for the molar conductivity, we use this formula of molar conductivity, that is lambda m equals to kappa by C. C is the concentration. So we know the concentration, and this equation is NCERT equation 2.21. So kappa is 248 multiplied by 10 to the power minus 3 Simon meter inverse. Okay, and divided by the C value, that is concentration, which is known for the concentration of our second solution. Okay, so that will be the molar conductivity. So molar conductivity will be 124 multiplied by 10 to the power minus 4 Simon meter square mole inverse. Okay, so this is how you can determine the molar conductivity and the conductivity for the second concentration solution. Okay, by using the formulas we have studied in this lecture. Thank you very much for joining this session.